Right, hello everyone. This is Dave Jewell and Darren Walters working with Magenta to talk about Femap today. So we ran a previous seminar talking about solid edge simulation, which is an embedded design analysis tool. But when that sort of hits the stops and there's not quite enough power, then that's when we make the step up to Femap. So what is Femap? It's a standalone system which enables you to prepare geometry, set up finite element models, invoke the solver, and then once we've got some results, drag them in and have a look at the results in a sort of usable way. It actually stands for finite element modeling and post-processing, although not many people really know that, and we just stick with the abbreviated name nowadays. So what is Siemens' product strategy for Femap? Well, the aim is to make this the best FEA modeler and pre and post processor in the market. We'll talk more about open simulation later, but this really relates to the ability of this tool to work with other systems in the marketplace, other solvers, for instance, and to share data with other systems. It's highly customizable, and it presents a really high level of value to the users. So virtual testing is really the name of the game with finite element analysis, and this little slide just demonstrates that an organization that integrates analysis and virtual prototyping into its processes will save a lot of time and money in delivering new product developments. That's obviously one of the benefits. There's numerous benefits to employing finite element techniques within the organization. Improved product quality, reduced material usage to reduce costs. The previous slide obviously talked about the saving in testing costs and improved time to market. But it also allows other things like greater innovation through being able to explore how your design is sensitive to different parameters. And then ultimately there's a reduced risk that things will go wrong once you've got your product out there in the market. So how have Siemens, what is Siemens' vision for Femap? Well, the vision is to provide the leading and most cost-effective high-performance FEA solution in the marketplace that's both easy to learn and easy to use. And the strapline that they've been using for this is real FEA made easy, because it is a big boy's toy, but it's made accessible to non-specialists as well as specialists. So how has that vision been realized? Well, we've just got a few bullet points here, which I won't go through in detail, but which really define some of the capabilities of Femap. So really, one of the aims of the game is to be cost effective in terms of the amount of functionality that's embedded into a single system. And I think the following slides will go into these things in a little bit more detail. So the key point I wanted to pick up from this slide is that it's a very, very widely used application. Over 20,000 customers around the world, wide range of industries, wide range of company sizes, from small to large organizations. I'm now going to hand back to Darren, who's going to run through a quick demonstration of using Femap and linking it to solid edge models.
Thanks, Dave. Right, so what we're going to do is this small assembly, and we're going to bring it to Femap, in this case from Solid Edge. We're going to run a linear static analysis on it, and then post-process the results and see how Femap links in with Solid Edge. There a button for Femap. which if I go to that, it will basically take this model and put it into Femap. Okay, so that's our model brought into Femap. One of the points I just make at this stage is I could have used the import function, so I could have gone import, and in here we have all the lots of standard kind of CAD imports like IGES, STEP, ACES, Parasolid. There's some native CAD readers as well. We're also maintaining a link to our Solid Edge model. So if I go to reference it, we can see that it's linked to those parts. And if these parts change, we can update the model, which I'll do when we finish this demonstration. Okay, if I would have assigned materials in Solid Edge to this part, they would actually appear in here also. But I've just gone through at a much more basic level, and so I can show the building up of materials and properties and that kind of thing. So what we're going to do is just start this model off by creating a couple of materials, and then create some properties for those. So before I do that, we don't want to run the analysis on all the components here. There's several bits in here that aren't of interest to us. So we've got to set the brake pad on the disk or the reader. So we actually just want to do the analysis on those three parts. So let's just get some materials. We're going to create an aluminium part, load it straight from the aluminium that comes with the software. Then we'll just load in also a steel component. Okay, so we've set up two materials, and then we're going to set up some properties. Virtually everything I do in this demonstration will be used in this model info tree and the post-processing toolbox later on. Although we've got lots of commands and menus, they spent a lot of time streamlining the interface over the last few releases, so we can do a lot of what we need to do at a kind of much more friendly CAD style interface down the left-hand side here. So we just set up some properties now for these three components. And this is where I basically assign them to the materials. I basically pick what kind of element it is. So lots of 20 or so different types of element we can define here. The reality is we probably only ever use half a dozen of these or something like that. But we've got things like beam elements, plate elements, composites, solids, rigids, masses, etc. All those kind of elements we can define. We're just going to define some solid elements. And it's a good idea to actually assign different properties to different components. It makes showing and hiding components at a later stage much more easily done. So I'll give them some names. You don't have to do this, but again, it's good practice just to type in some names as we go along. Helps later on. And we'll just change the shaft component to have a steel material. And I'm also going to define a bolt as well. We're going to create some bolts in this later on, which are actually going to be beam element types. So we can just very easily just pick a circular section, and then we can define a bolt in that way. Okay, let's set up some loads constraints, and we go through meshing and setting up the connections. So what we're going to do is just create a load set. So again, I don't need to name these, but it's usually a good idea to do so. We'll have a braking and a bump case for this one. And all I'm going to do is just apply a force to that shaft. So I'm just going to apply a force on a surface. So we can use the geometry here to apply the forces to. And I'll just apply a force in the y direction, the positive y direction. We can align this with different directions, normal to surfaces, by specifying a vector, all the usual kind of methods that we can define a force vector with. Let's also assign a force to this face here to represent the braking load. So let's just pick that face there. And just a quick note about the different types of loads we can apply. Obviously, we've got forces, which we applied before, moments, bearing forces, torques, pressures, etc. All those kind of standard and those that you would expect to be able to apply to a model. So let's just put 12 kilonewtons in the positive y direction for the brake caliper. Okay, so we've applied some loads. Let's just say constraint set, and let's apply some constraints to this model. What we could do, if we're going to do this as a kind of real job, what we'd probably do is define some rigid elements in these joints and actually represent them as ball joints. Very, very easily done. But for this situation, all I'm going to do is just restrain some of these faces within these locations here. So just apply directly to surfaces. I'm just going to fix that lower in there in all directions. If I right-click the previous command, I repeat the command again. So that one in that location there, let's just restrain it in the Z, and in this location here, let's restrain it in the X and Z. Okay, let's just save it as we're going along. Always a good idea. So we've got some loads and constraints on. Later on I'll put a bolt load on as well, but that's all we can do for the moment. Let's mesh it then. So what we're going to do is just apply a tetrahedral mesh to these components. Now I could just pick a component, mesh, and then pick the property that I've defined earlier. What's a better way of working? It's just to assign as an attribute those mesh properties to the individual components. So basically we just set the property and link it to the solid component that we have, like so. Okay, so let's just set up some mesh sizes. So we can do that. I tend to just do it within this toolbar. So for those two components, I'm just going to set up a 4mm mesh size. If I switch the lines on, we can get a preview of what that mesh size will look like. I don't really care about the caliper. It's a bought-in component, so I just wanted to transfer a load. So I just specify quite a large element size for that. Okay, so to mesh it, we'll just do it in the menu up here, in the toolbar up here. We can mesh directly from this menu as well, but it's in this particular example, going three components. I'll switch mid-side nose off because it's a demonstration, so we'll speed up the solution. And we've already assigned the attributes, so we'll basically put the correct property in the correct solid component. Okay, so that runs through now and sets up and creates the mesh. We'll just set some random colours for these different properties. Play with property, and it will trim them. The visual representation of which of different colours for different properties. Okay, so a couple of other things I need to do for this model. Firstly is I need to set up connections. So to do that, I'll switch the mesh off. In fact, let's switch all the finite element data, like so, and just switch the surfaces back on. What the connections are, so I can automatically define connections between these parts. So if I just go to automatic, pick the caliper on the upper right, and I can determine whether it's a contact. So in other words, a no penetration contact. So the components can slide relative to each other, can lift apart, but can't penetrate each other. So we'll just select contact for those two. And for these two components, we'll just select a glued contact. So we're just going to glue the shaft into there. We could model that with an interference and look at the stress from a pressing operation or something like that, but we're just going to glue it in for this situation. And let's just put friction on. So I can just go back and edit anything to do with those connections. I'm just going to put a friction coefficient in that joint as well. Okay, so the final thing that I'm going to do to this model is I'm just going to define some bolts in these locations. Okay, so the way we're going to do that is a fairly standard way of representing bolt, which is some rigid elements to represent the head or the nut or the threaded area, and then a beam element to the actual shank of the bolt. If I just switch the sizes off, do is just define some rigid elements in this location and the bolt head. It's also a good idea just to off the solid element so that when I actually mesh it, I'll just display the new rigid elements. Just go model, element, type is a rigid. I have a new node at the center which we'll use to connect the beam elements. And then those two faces there. So that's our rigid element. Being the other end, just, process for the other bolt. Okay. So we've got the beginning of our bolt representation, and we're just now going to put some beam elements between these two central nodes on both of the bolts, and just to create the bolt element, the beam element, which will represent the bolt. So, a number of ways of doing this. I'll just use a particular mesh between command, which is quite good for doing this, and we'll just pick the two nodes like so. We just need to align an alignment vector for the beam element. And we could do the same for the other, but what I'll do is I'll just show a slightly different way, is I can just basically copy these elements. So copy these three beam elements from there to there. So not limited in Femap. We can go in and obviously work with the elements directly, as you can see. We're not limited by just using CAD geometry or anything like that. So the final thing we'll do is just do and then we can switch back on our solid elements. So one other thing that I mentioned before that I just need to do to this model, and it'd be a good idea again just to hide those solid elements, is just to apply some preload to these bolts now, and that's just a load. So all that we do is, we've got these options available, so we can apply loads to nodes or elements directly. And in this case, I just want to apply a preload to a bolt. So the preload I've calculated about 25 kilonewtons. I'll just apply those two bolts there, and if I put the loads back on, we can see those applied. Okay, so let's go ahead and run the analysis. So basically, we just set up an analysis set. So it's not until this stage we actually tell it what type of analysis we're going to run. So in this case, it's going to be a static analysis, but it could be a modal analysis. It could be heat transfer, advanced dynamics, nonlinear, whatever solvers we actually happen to have. And not only that, is we define also what solver we want to link to. In this case, NX Nastran, but you can see it links directly to lots of industry standard solvers. And the only other thing I'm going to do is just tell it to use four cores in, and because it's a demonstration, we'll just turn the check off and then press Analyze. The solution now, and we can see that it brings up the analysis monitor down the left-hand side, where we can obviously monitor what's going on with the solution. So, for example, we can look at the contact convergences it's running through. It's extremely useful, especially if you have a very, very complex model, to be able to monitor whether you're achieving a solution. So this is the kind of thing you want to be seeing in this window here. Basically, the contact is solving, is iterating to a solution. We've also got the sparse matrix solve window as well, which is again very useful to see how close we are to come through to the end of the solving. So that's now solved. It's generated the results set, and we now have some results there. So if we just hit the deformed view, we get an animation showing what's actually going on with our model. The results, in fact, helps you when you go into put the result into maybe do screen grabs for your report or whatever. So background which I've got saved. You can save multiple views in the interface, and that helps us to look at the results. So let's just look at a contour plot of our mice stress plot as default, which you can see just there. If you don't want to see the filled edges, we can. I tend to prefer them being shown. Okay, I mentioned earlier that it was a good idea to put the different components in different properties, and very good reason for that is I can just switch them off at this stage. So if I just want to look at the results, right, which is the component we're actually interested in, thing to do. We don't have to use groups or layers, which we do have access to, but we don't need to use them then. Another good idea is we lots of things we can do with the post-processing. One of the things that's quite a good idea is just to change the scale down the right-hand side there. So let's just put a maximum of 50 MPa. That just helps highlight where our high stresses are. Okay, so let's just look at the data table. We've been able to put data into the basically be able to look at data, tabular data for our model. There's lots of things we can do with this. One of the things we might want to send a summary to this. Okay, so we can just send a quick summary to that, which gives us a summary of maybe the peak translations, the peak, etc. But what I'm going to actually use the data table for in this case is let's just have a look at what the bolts are doing. Very, very useful thing to do to our model. So how the preload's changing when we apply that load. So if we just select a couple of elements in there, add some results, add the result set, so axial force in the beam, and we can look at what actual force we have in the beam after, or the bolt, after we've applied the external loads to it. So they're varying slightly from the 25 kilonewtons that I actually applied to the model. The other thing, if we just hover over an element, one of these elements, for example, then it'll come up and tell me what the stress is at those locations. So it's about 180 MPa we've got as a peak nodal stress there. Okay, so we could obviously go through and look at more post-processing here, but what I'll do instead is let's now go back to the edge and make a change as how that affects what we actually see with our model. With Edge, what I'm going to do is to the upper how the two programs are together. Just drag spaces. We've seen some high stress there, so let's just add a mirror to that location. It's just space as well, and let's use the radius in here as well to probably put a bigger radius. Okay, so this back to our model there. Save the model. Now when we go, let's just turn off the results. Any sound. If I now go back to references, see that it's noticed something's changed with the model. Basically, it's been updated. The parts have been updated, and so we could do nothing for this, or we could save it as a new model, Rev 1 or whatever. Or what I'm going to do is I'm just going to reread the file. So in other words, I'm going to just update the geometry in Femap. So we have a choice here. We can either update the solids in here, or we can create new ones, which can be a useful option sometimes. If you've made some very major changes to your model, such that loads you've applied no longer link to faces. So if you've deleted a face in the solid edge model, that so that a load can no longer be applied to it in Femap, it's quite good. It can be quite good idea just to recreate the solid and just reassign the load at this stage. But I'll just say, don't want a new solid. I just want to update the current ones, and then it will do some work with how to reassign the mesh sizes. So I just click OK to that, accept the defaults, and now all our references are up to date. Models changed, it's deleted our mesh, but all we actually need to do, all our loads are still there. If I look at the loads just with the highlighter, you can see it's still good applied. What you need to do now, mesh, and resolve the analysis. So if I just click the mesh, pick the 3 parts, I turn mid-side nose off again. Okay, all our connections are still set up and everything. We'll just do another move to reconnect the bolts back in. All we should need to do is just say analyze. I've actually got the 2 of them hidden from when I was looking at the results, which is why it appears to have only meshed the component. But if I just switch these back on, whilst it's solving, that's why they weren't appearing on the screen. So it's just going to run through the solution again. Again, we can monitor the solution as we go. And at the end of this, we'll end up with a new result set based on the revised geometry. So again, just takes a moment or two to run through that. So it's actually an iterative process because it doesn't actually know how far to shrink the bolt. It has to do it over an iterative process. In this particular example, it takes 2 attempts to get the correct preload in the bolt, just basically by some kind of shrinkage being applied to it. So we can just run through the analysis again. And just again, like so. Let's just the new result set there. Based on thicker geometry in there. Probably still a bit of work required, maybe a bigger radius in that region, but it's an improvement, and it's just showing how we can iterate to a design by linking solid edge to Femap. So that's all I'm actually going to show on this one. I'm just going to let Dave continue with the slideshow, then we'll come back in a minute and we'll look at a bit more meshing on that component and some meshing where we can show the meshing toolbox and that kind of thing. But I'll pass back to Dave now.
Brilliant, thank you, Darren. Well done. Okay, so just sort of returning sort of a sort of more of an overview type discussion. Femap ships with a really good cost-effective bundle called Femap with NX Nastran Basic, and this includes the majority of the kind of solution types that most users are looking for on a day-to-day basis. So we're talking linear statics, normal modes of vibration, buckling modes, heat transfer, some basic non-linear, contact, you've seen that demonstrated, glued connections, etc., etc. But then, because this is a scalable solution, there's a number of more advanced solver modules that can be added on for advanced dynamics type analysis, advanced nonlinear rotor dynamics, and right up to CFD and advanced thermal analyses. Now, the user interface has been really improved over the last few releases to make this product more accessible to the non-specialist. So this gives you much better productivity to get these products to market more quickly, and a reduced training overhead to learn and use the software. And we truly believe that the Femap solution, standard bundle, offers the best functionality price point in the industry. So the next slides just go through a number of the kind of automated features that are available in Femap. So this slide shows that if you're bringing in, I mean, what Darren demonstrated just now was working with native solid edge geometry and using the link to recognize a change made to the original data. But very often, Femap is used as a downstream application for using CAD geometry that's been developed by another engineer or even another organization. So there may not necessarily be, the geometry may not be coming in a quality that's suitable for analysis. But Femap gives a toolbox which allows geometry to be cleaned up and small features to be removed, patched together, etc., like that. So there's a number of different types of meshing that can be carried out, from the automatic tetrahedral meshing, which is great if you're dealing with 3D solid models that have been developed in CAD. And because the auto mesher deals with it can deal with a wide range of different geometry types, but it will produce an efficient, robust mesh with kind of minimal interference, as it were. But if you're dealing with complex assemblies or fabrications, then there is the ability to do different types of meshing. And the picture on the right here shows a shell mesh of structure which is quad dominant. So in other words, it will focus on doing quad shaped elements. Also, when we're dealing with structured meshes, 3D structured meshes, then Femap can automatically recognize extrudable areas that can be hex meshed. And then it automatically links the adjacent regions together by merging nodes. So I'm going to hand back to Darren now, and he's going to carry on with some further demonstration.
Okay. Yeah, what I'm going to do then is a couple of demonstrations here. First of all, actually just continuing with some with this particular model here. So what I'm going to do is meshing work on this. So let's just delete all the elements in the model first of all. So I'm just going to show how we can use the meshing toolbox to maybe improve the mesh on the upright component here. So say delete mesh. And then it's going to hide those components. Let's just assign to this like we did before. And instead of meshing it as a solid, we're just going to mesh all the surfaces. So we're just going to mesh the surface this bit solid with triangular elements. And there we have a surface mesh in the model. The reason for doing this is it will allow us to edit the surface mesh and later create a high quality solid mesh. So I'm just going to use just a few of the functions in this particular toolbox here, just to improve that we can see straight away, where we've got a very small feature here, which is creating this line of very small elements, which probably not going to affect our results massively, but might be a good idea just to remove that very easily just by suppressing that edge. So if we just say suppress feature suppression curve, the same on the bottom, you can see what it's press those little edges, it's allowed us to put a full element in there and basically span across that feature that we didn't like particularly there. So maybe we could do, but the meshing functions with the toolbox now. After we've gone through and run the analysis, identified some regions that we want a finer mesh in. So if we look at this region here, just an example, if we just go to mesh sizing, do is just clicking on line or edges, mesh density on the edges that we make, like so. Of improving our mesh very quickly and efficiently. And not only that, we can set spacing options if we want. So we can put a finer mesh at this end. Okay, so let's do it down here. So maybe we'll put a mesh in this region as well. It could be quite critical to others. Just improving the mesh in regions. We can also look at the mesh qualities we're going through. I'm just happen to be looking at the Jacobian, but I could look at aspect ratio or a whole range of other mesh quality options. And one of the things we can move nodes, move elements around, or move nodes around and maintain the link to the surface so that we can improve the mesh. If again, if there's a particular feature that we want to really get very good results out, and we can do that. And for made all the changes that we want to, we can just go ahead and mesh. Let's put mid-side nodes on this time, and let's also just put mid-side nodes on the surface as well. Just push them to the surface. And then those changes that we made to the surface mesh we brought through into the solid mesh. Now to solid elements, which we can confirm just by looking down the left in the model info tree. Okay. So let's just load up another part of the component. We'll just do a little bit more meshing here for this particular component. A car chassis. The vast majority of it's been meshed, and I'm just going to go in and mesh some of the features at the front just to finish it off. So this is a surface model. This was generated within a CAD system as a surface model, but we could also have tools within Femap. There's a whole geometry creation tools with the geometry creation tools within Femap, and specifically there are some mid-plane extraction tools as well, which we're not going to run through in this demonstration. So mesh these with the meshing toolbox. So what we'll probably do is pick what size element, what property we want to associate with this mesh. In other words, what sheet thickness we're talking about. And we can just go in and just click on faces and just mesh them with that size. Or alternatively, the faces, the surfaces that we want to mesh, and just do them all in one go like so. Okay, so I'm just going through and meshing all those faces at the moment. Here, these particular surfaces for these brackets, I've actually put the wrong property in there. I actually wanted these to be 3mm thick steel. Okay, we can change the properties and modify command up there, or if we just remesh them with 3mm, it won't put a mesh on top of the other mesh. It's intelligent enough to know that it only wants one set of elements there. So we'll just basically change the property in this way. And then we've got the sheets, the plates on the top of other plates. That one there, sorry, we'll do that. It's 4.6mm. Let's just go back and change it to 3. There is actually an undo feature, which I could have used there if I accidentally meshed the wrong one. One of the nice things I'll just briefly show in the meshing toolbox or some kind of location like that, you want a better mesh quality around those faces. So there's a nice little tool in here which allows us to create what is called a washer. So if I just click on those edges, it'll basically go through, as you can see, it'll put a nice series of regular quad elements around that hole. And it's changing the underlying geometry. See, so it's actually splitting the geometry. Model off. Create some rigid elements to connect this beam into those brackets. So we went through this before, very simply, element, a rigid element, from that node there to all the nodes on those curves. Okay, and we'll just do the same again. I've got a white background and white elements, so that's not a problem. I'll just change that in a moment. Okay, so let's just go back and change the element color to red, something like that, so I can see it. There we go. One other to mesh quickly. So we've got some aluminium panels in here. So let's just go through the meshing toolbox again. Mesh surface, aluminium. And let's mesh those there. What item is just to put a much smaller, larger mesh size in the middle. We don't really care about that. Just improve the efficiency of our model just by changing the number of elements there. So we can just do that under mesh sizing. I don't know, 10 elements on these edges. Those edges now. Like so. There we go. So we just put a coarser mesh in there just to help with the efficiency of our model. So, analysis set already set up. So we just right click there and say to run that analysis set. So the model's got almost 130,000 nodes in. It's a shell model, plate model primarily. It's got some beam elements in as well. Side here is the axle at the back with some beam elements linking it in. We can release degrees of freedom of the beams to represent pin joints, that kind of thing, just to get a more accurate model and to get the loads transferred through the chassis in a much more accurate method. What we're doing is we're just applying basically a couple, two force on the back just to twist the chassis to look at the rigidity of it. So that's now solved. You can see at the bottom of the screen there, the window down. And we're just looking at displacement. It's just doing we see the chassis. Okay, so it's just a little bit about the meshing toolbox and how we might use it to help us create a nice shell model. So I'll control back to Dave now, and he can do a few more slides, and then we'll come back in a bit to do one further brief demonstration with some beam elements.
Thank you, Darren. That was really good. And that shows really that using Femap, if you're coming from a CAD embedded FEA within CAD background, then this is a new way of thinking. There's two sort of key points which sort of jump out from that demonstration. One is that a complex structure like this sports car chassis couldn't be modelled. If you took a solid model of it and tried to mesh it with 3D elements, you'd be there all day trying to obtain a solution, and I wouldn't really fancy that. So idealizing it into, we're just looking at the the surface representations and doing shell modeling gives you a real performance advantage, productivity advantage. But the other thing to think about is that you're not just sort of firing off a CAD model at the auto mesher and seeing what comes back. You can work in that way within Femap. The first demonstration really showed that the auto mesher works very well with 3D geometry. But the fact that you can mesh your assembly or your structure piece by piece and stitch all the bits together, and then you can adapt the mesh on the fly is a really sort of new and powerful way of working. So, okay, so now just very briefly move on with a few more slides to talk about some of the other capabilities of Femap. So the way in which Femap deals with assembly modeling and how it handles connections between components. There's some really good automated tools for detecting the contact surfaces or the regions of the assembly where one part touches another, and then you can set up a variety of contact methods that defines how the behavior works. So you've got linear bonded contact, and you've got non-linear contact, which really simulates as just a much more realistic contact method, which looks at low transfer as the parts come into contact with each other, but it allows separation. We've also got some powerful beam element modeling capabilities in Femap. Again, when we're doing idealize, this is a further level of idealization beyond shell meshing, where you take a structure and a beam model structure, and you represent the beams with just line elements, but then you define your section properties of those lines or beams, and you can define quite complex section properties in which the beam sections are section properties are calculated automatically, and you can have user-defined beam sections or off-the-shelf library sections. And then we'll see further on, when it comes to post-processing, the way in which the data can be mapped back onto those beam elements. So when you're dealing with beam models, 1D and 2D element types, there can be issues with actually visualizing what's going on, but there's some really powerful tools in Femap that enable you to see what's going on. You can shrink elements, although beams within the maths of finite element analysis are just line elements. Being able to visualize beam sections in 3D mapped onto those is very helpful, and same with plate sections as well for 2D elements. We've got a very powerful composite modeler in Femap, where you can define layups and ply directions, etc. So there's a really powerful layup editor that enables you to define all the ply orientations and thicknesses, and that sort of reads across into the post-processing when it comes to analyzing the results and looking at what's going on in a layer-by-layer basis. Now, there's the NX Nastran solver, which ships with the standard bundle. Well, Nastran is a name that many people would have heard. It's been around since 1972, originally developed by NASA. And again, there's an acronym embedded in that name. It comes from NASA, Structural Analysis. And it was actually developed to help design the Saturn V launch vehicle. This tool has been developed over the years by a number of different developers, and Siemens obtained the rights to develop this software in 2003 as a sort of parallel development route from MSc. But it's interesting that the Femap itself is probably the most widely used pre and post processor for the Nastran solvers, regardless of who developed the solvers. So Femap, its open simulation strategy is to enable it to interface with a wide range of commercially available solvers. Some of them listed there. Most people have heard of ANSYS and Abacus. TMG does thermal and fluid flow solvers. So post-processing then, we've seen quite a lot of what you can do with post-processing, visualizing the results. You've got full control over which results you're even going to display before you set up the analysis. And one of the things that we haven't seen yet is XY plotting is a really powerful way of visualizing what's going on, as well as the usual contour plots. And all the post-processing tools have been consolidated into a single post-processing toolbox. Again, this is the development of Femap has really streamlined the usability. In the past, a lot of these functions and features were hidden away in various menus and toolbars, but now the sort of ethos is to be able to drive everything from some simple toolboxes. We've seen the meshing toolbox in an earlier demonstration. The post-processing toolbox puts all the tools in one place, which obviously improves the usability of the software and reduces training time. Earlier we just discussed briefly the beam modeling capabilities of Femap. So when it comes to actually looking at results on from beam models, we can you can see here a very complex beam section. This is a section through a beam, and the stresses can actually be mapped onto the beam sections, even though it's only a 1D element has been used. The stresses and other results values through the sections can be calculated and displayed in this 3D fashion, which really improves visualization of what's going on. One of the other clever things you can do in Femap is transfer results from one analysis to another. So an example here is to take pressure results from a CFD analysis and map them onto a shell mesh, a structural mesh, and look at how those pressures influence the structural behavior. I'm just going to hand back to Darren now for the next demo.
Thanks, Dave. So the final model then that we're going to run today is we're just going to look at a simple beam model, basically the chassis that we were running before, and we're just going to look at that as if it's constructed from beam elements. So we'd probably do this stage before the shell modeling example that I showed before. So this is a very good way of actually, in this particular case, determining where we want to put our beam elements, how we actually want to construct this chassis so that we get a good rigidity. So these are all the beam elements, and what we're doing at the moment is we're visualizing these with their section on. We've generally got inch square tubing here. And we've got some circular sections as well. We've got some smaller 3/4 inch sections as well. So at the moment these are being displayed with their thickness and cross section. If I turn those off, basically as you see a line model pretty much, it's constructed of beam. I've also got in here, which I've got in at the moment, some aluminium, some of the sheet materials as well, all the plate materials as well hidden where we're putting the aluminium panels on the side of it. We'll leave those hidden, and we'll just continue with the model like we've got at the moment. Two forces on the back, and then we're going to look at the displacement of it to give us an idea of the rigidity. So the model's already set up. We'll run through a bit more in a moment, but all we're going to do at the moment is it. So one very nice thing about beam element models is they run extremely quickly. Because we've only got 15,000 nodes in this model compared to the nearly 10 times as many in the shell model. So that's run. If I just put the thickness section again and plot, and maybe look at a displacement as well. So this is the post-processing toolbox that Dave mentioned a moment ago. So if we look at translation, we get 9 with the model. We can see that quite a lot of deformation, quite a lot of displacement occurring at the front. So it's probably an area where we would want to go in and put some additional chassis members. Way of doing that, and show why at this stage of a design that it's very useful if we can visualize something or run something with beam elements. It means that we can change the model very, very quickly. Do a frame, and then look at the results, look at the difference in the results. So numerous ways of doing this. I could put lines in and mesh the lines. What I'll do is I'll just use a useful command in here, which just allows us to mesh between 2 points. So if I just put in some 3/4 inch box section between that location and there. Okay, we just need to orientate a vector. There's a number of ways of doing this. To basically align the direction of the beam element. Let's just do the same command again. From that location. Like so. And then let's also put that in between along the side there. So again, we just use the same command again. Just say right click this command. That's the best way to do it. Let's put some tubing in this time. Again, let's put it 10 elements. That corner there. Right click previous command. Exactly the same again. Because it's easier just to just click the locations again. Okay, let's look at thickness. I guess just needs to do a node merge. Those nodes, and it's found eight coincident nodes as we'd expect with the ends of the beams. Okay, so let's just say analyze again. And we can just run through and see what difference that design change has made. So again, runs very, very quickly because the beam model allows us to get results and change very efficiently. Let's just look at how the results set. So we're 2 millimeters before, now we've got 1.36 millimeters. So we've made a significant improvement to the rigidity by putting those members in. Have a look at some of the other functions that we can perform with when looking at beam elements. Okay, so if we go to a beam cross section and pick an element element. We'll pick one of those ones at the front there. Let's just have a look at, I don't know, von Mises stress maybe, and click apply. So I just need to change the thickness. Let's just go to advanced posts again, beat section, got an element picked. And then so that allows us to look at the stress through one of our beam cross sections, and we can element. We've got some quite complicated cross sections there to be able to look at how the stress actually varies through the section. Okay, so just a very brief demonstration on how we build a model with beam elements, or how we can, in this case, modify a model with beam elements, run through it, and then look at stresses through sections or global results such as displacements or whatever. And what we're the two displacements at these locations is through some very simple trigonometry. We can just calculate the angle. Because we know the torque applied to it and the angle, we can get the effectively the chassis stiffness from that. Okay, so I'll just hand back to Henry to just run through the last couple of slides.
Thanks, Darren. That's great. Again, it shows just a different way of thinking using Femap instead of CAD embedded analysis. And this type of technique used early on in the design cycle, it enables you to sort of get the basic structure sorted out before you sort of move on to sort of fabrication details. So we've looked at a lot of the sort of standard capability from Femap, but there are all these powerful extensions, solver add-ons that are available, such as advanced nonlinear, that enables you to deal with sort of deformable materials. I mean, this looks like some kind of metal forming, or some deformable fastener. And you can look at high velocity impact types of analysis as well. We've got design optimization tools and topology optimization. Topology optimization is quite interesting because you can define a set of loads and a block of material, and the analysis goes away and carves away the material that's not actually pulling its weight, so to speak, not doing any work. So you end up with an optimized structure for handling that load set. We've got the thermal and advanced thermal solvers. The standard thermal solver allows you to simulate conduction, convection, and radiation, and define some thermal boundary conditions at the perimeters of your structure. The advanced thermal solver brings in duct flow, radiation, orbital modeling, so it's actually quite widely used in the satellite industry. And then there's the flow solver, which adds fluid flow capability to the thermal analysis. Something that we haven't really had a chance to talk about because we're really kind of time limited is the API, the ability to automate repetitive sequences of commands and define write macros effectively that enable you to run through the same types of function over and over again in a really efficient way. So to sum up then, Femap with NX Nestone is designed for analysts, but it's easy enough to be used by CAD engineers. You can bring in solid edge models, 3D models, and auto mesh and solve in much the same way that you would with an embedded CAD FEA system. But you can move things forward to generate idealized models of complex structures, as we've seen. The the solver bundle that comes with E600 or E601, and these are codes for, which represent whether the software is node locked or networked. So there's a couple of licensing options for the software as well to make the most use within an organization. There's huge capability in the off-the-shelf system, but the ability to expand that capability with some of the add-on solver modules. We've got this really powerful post-processing toolbox, which allows really detailed interrogation of results from the model. And you've got a customizable API for setting up this setting up the interface so that it can be that repetitive tasks can be automated, or even so that you can have simple procedures that can be operated by less skilled people, shall we say, that are sort of developed in-house to enable less skilled operators or to run through some standard types of analysis. So that's about it. We're not running this presentation live, so any questions, well, get in touch with Magenta, and they'll put you in touch with us, and I'm sure we'll be able to answer any questions that come about.